Okay, so we're doing kind of the highlights reel for chemical behavior of gases, but a few things that you should know. Any gas, hydrogen, helium, nitrogen, carbon dioxide, oxygen, blah, 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 no matter what its molecular mass is, none of that matters. If you are at STP, 1 mole of gas is 22.4 liters of gas. It's a standard molar gas volume. And if you look up at the mole cube up here, it just so happens that this box, I probably can't reach this today because of my back, this box has a volume of 22.4 liters. I don't know if you can see the side that says 22. You can't, can you? Okay. So at STP, now, what's standard temperature and pressure? We just did this, yeah. 273 Kelvin, and what pressure? 1 atm or 760 torr. So under those conditions, at STP, and only at STP, any gas, no matter what gas it is, has that volume of what? 22.4 liters. So that volume, it would fill that box. And today, by the way, pressure in the lab is, 758. We've dropped a little bit. We were 761 yesterday, 763 2 days ago. So we've got some dropping pressure. Okay, let's go to 337, and we're going to actually do a practice problem together. So this gives us 3 questions, and we'll start off with just that first one. What's the mass of 1.33 times 10 to the 4th milliliters of oxygen gas at STP? What do we know? What do we need to know in that problem? We know the volume of 1 mole of oxygen gas at STP. This is just a standard, it's gas stoichiometry basically. What do we start with? We're doing a factor label. Given, always. So our given is 1.33 times 10 to the 4th milliliters of O2. And this is where I always write, so that I don't screw this up, I write that right in my factor label at STP, because that tells me I'm looking at a molar gas volume problem. Well, I want to know the mass. This should be easy, right? What units do I need on the bottom to cancel? Units in chemical. Milliliters. Milliliters of O2. Okay. Can I go right straight from milliliters to mass? My molar gas volume is in liters, so I first have to do a milliliters to liters conversion. So I know here I'm going to need liters of O2. What units, what chemical in the next space to cancel? Liters of O2. And from liters of O2, since I'm at STP, I know how many moles that is. So I have a mole relationship. 1 mole of O2 at STP is 22.4 liters of O2 at STP. What's my relationship between milliliters and liters? 1 milliliter is 10 to the negative 3rd liters. Okay. So, what's my next step here? If I want to get into mass and I have moles, what goes on the bottom to cancel there? Moles of O2. Can I go straight from moles of O2 to mass of O2? Yes. What's the mass of 1 mole of O2? 32 grams. 32.00 grams of O2 in 1 mole of O2. Okay, let's do the math. Okay, I'm getting 1.9 times 10 to the 1st grams of O2. That would be 19 grams of O2. Correct answer is 19 grams of O2. And I can actually have one more sig fig, so it would be 19.0 grams of O2. Okay. This only works at STP. This only works at STP. So at STP, it is 22.4 liters per mole. Once you depart from STP, it all changes. So how often do you think chemical reactions run at STP? Yeah. At 0 Celsius? Are you running a lot of reactions in rooms that are at 0 Celsius? No, not so much. So it's most useful to use this when we're converting. Remember how you converted your volume of gas down to your volume of gas, you converted down to STP. Well, now you have a volume of gas at STP, you can figure out how many moles of gas you produced using that. Okay, so if we're going to do this, calculate the volume of dry hydrogen gas that would be produced by 1 mole of magnesium at standard temp and pressure. Do you have the overall chemical equation for this reaction? What is it? Mg plus HCl yields MgCl2 plus H2. Balance it. Done. So if you had 1 mole of magnesium reacting, how many moles of hydrogen gas would you expect to produce? 1. 1 mole of magnesium, for every 1 mole of magnesium, Gesundheit, that reacts, we're going to produce 1 mole of H2. Now they're saying at standard temp and pressure. What's the volume of dry hydrogen gas that would be produced by 1 mole of magnesium at standard temp and pressure? Well, 1 mole of H2, and I'm going to write in there at STP, has a volume of what? 22.4 liters. What's your volume of dry hydrogen at STP? 22.4 liters. Oops, I didn't put in there of hydrogen. That's a lot more gas collection space than you have in your Biarette, you'll note. There's a reason that we severely limited the amount of magnesium that we used, because if we use too much magnesium, we empty the Biarette and we can't track the amount of hydrogen gas that's produced anymore. So, using that, could you figure out how many moles of hydrogen you produced based on your volume? Yeah, you could, because you've adjusted your volume down to HTP. There are techniques for figuring out how many moles of hydrogen gas you produced at the conditions we had in the lab, but you don't know that yet. So now that you've got it adjusted to STP, you could very easily figure out how many moles of hydrogen gas you produced. Oh. Okay, so we answered that in an ideal scenario. We said in an ideal scenario you're going to get 22.4 liters of hydrogen gas out of 1 mole of magnesium at STP. Now let's see how good you are. So how would you figure out, based on the volume of hydrogen gas that you produced under your lab conditions, how would you figure out the volume of dry hydrogen gas that you would get from 1 mole of magnesium at STP? Do you have a volume of H2 that you produced at STP? You do. Do you have the number of moles of magnesium that you used? So, if you take the volume of hydrogen gas that you produced at STP, dry hydrogen, which you've calculated, and you take the number of moles of magnesium you used, what you should get is the volume of hydrogen gas that you would produce at STP. You're going to compare that to the 22.4. How good are you? Go. right, so we're going to do a sample problem. Taking your actual data and looking at how many moles of magnesium you had, which I think, did you calculate in this somewhere?
Yeah.
Okay, so converting that to moles of magnesium. Magnesium is 24.10, is that correct? 24.31? Okay. Grams of magnesium in 1 mole. Okay, that's not a lot of moles of magnesium. Tiny amount of magnesium. What was your volume of gas adjusted to STP? Okay, so we did a little bit of rearranging here. We've got 11.4 times 10 to the negative third liters of hydrogen. 11.4 divided by 0.822707. Oh, that's terrible. Okay. That's terrible. Huh. You're getting like 13 liters of hydrogen per mole of magnesium. I think you have some measurement issues.
Yeah.
Yeah, I think so. Okay. Who's getting a closer? Okay, so up to now, everything that we have talked about has been dealing with pressure, volume, and temperature, and the number of actual particles of the gas don't change, right? That was the physical characteristics. Well, now we want to think about what happens when we have a gas as a product of a reaction, or when we have a gas as a reactant itself. So one other quick shortcut, and this is, we're going to go back to one of my favorite reactions. So this is the combustion of methane. We've got it balanced. What is true if we put in the state information for all of these products and all of these reactants? What state are they all in? Gas. Every single one of them. Gas. Gas. We could go on. Gas. Gas. I mean, there's water produced in combustion, but it's in the vapor form because is this happening at a temperature where water would be a liquid? Heck no. This is happening at, I don't know. What's the temperature for the combustion of methane? I don't know. So this thing is happening, you know, at something like 1950 Celsius. Hot. Is this at STP? Heck no, STP is 0 Celsius. So we can't pull our little trick if we want to know what volume of gases we're going to produce. We can't pull our little trick of, oh, at STP it's 24 point something liters per, 22.4 liters of any gas. But there's another little trick in our tool belt, and that is the idea of gas volumes. If every single thing in a reaction is at the same conditions of temperature and pressure. Now, if these things are reacting together, are they at the same temperatures and same pressures? Yeah. They're all at the same temperatures and same pressures. We can use the coefficients as gas volumes. Okay? So for any, if we say 1 liter of CH4 combusts, how many liters of water vapor are going to be produced? We can use those coefficients on these as volume measurements, and it's 1 liter to 1 liter. So for every 1 liter of methane, we get 2 liters of H2, so this reaction would produce 2 liters of water vapor. If we had 500 milliliters of methane, could we figure out how many liters of water we're going to produce? Yeah. The coefficients basically in reactions between all gaseous reactants giving you all gaseous products act as volume ratios. So we can substitute those for mole ratios. That is as long as everything is in the same state and under the same conditions. Now, there are reactions where we have solid reactants and liquid reactants, and yet we generate gaseous products. Can you think of one? Have you done one recently? Solid magnesium plus liquid hydrochloric acid yields gaseous hydrogen and aqueous magnesium chloride, perhaps? Why, indeed! Huzzah! Okay, we have situations like that. In that case, we can't use volume ratios because, and somebody tried to convert moles of magnesium into a volume. It's a solid. It's a whole different thing. It's okay. It happens, especially when we're all fuzzy. We only use these volume relationships when we're talking about the gases. It's, volume is way different for solids and liquids. So we don't think about we don't think about volumes for solids and liquids in terms of the stoichiometry. We think about mass. But with gases, because their volume is not fixed, we have to use some other tools. So this is one nice shortcut. Here's the next thing. This is the ideal gas law. We're not going to do a whole lot with it, but I want you to be aware of it. We're, if you hadn't noticed, kind of skimming all the stuff on gases. We're then going to talk a little bit about solids prior to your trip to the museum because our main focus for chemistry and going to the museum is crystalline solids. So the ideal gas law is just what it says. It's a mathematical relationship between temperature, volume, pressure, and there's that fourth piece. If the number of moles is changing, we now have a way to factor that in. You can do the derivation if you're one of those people who really likes to derive formulas yourself. In physics, I do that. Here, I don't. The ideal gas law is PV equals nRT. PV equals nert, 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 nert. It's fun to say. PIV equals nert, nert. It'll help you remember it. If you need to remember it, it's a good mnemonic. It's stupid and irritating, but it works. So, you know what volume and pressure and temperature are, PV and T. N is number of moles. That's not all that hard. We very often in math use N to equal the number of something, so that's an obvious one. R is what we call a constant. You can think of this as a fudge factor if you'd like, but it's this sort of ratio relationship between these things that you have to insert to get the math to work. Okay, so R is equal to 1 standard pressure, 1 atmosphere of pressure, which is 22.4 liters, if it's 1 mole at 273.15 Kelvin. We haven't used the 0.15, we usually don't. But what that gets you is an R value of 0.08258784 liter ATMs over mole kelvins. We round that to 0.0821. Now here's the thing. There are 5 different versions. Wait. Torr, ATMs, pascals. No, 4 different versions of the ideal gas constant. 4 different numbers. Because they're based on this relationship, you can always derive the ideal gas constant if you know the units. Because it is a standard pressure. So you can use, you can use the 1 ATM, you can use the 760 torr, you could use 101.325 kilopascals, you can use any of those, but you're going to get a different ideal gas constant. Page 342 in your book has got a chart of all the ideal gas constants, but what we're going to do is just do one practice problem. What this makes really easy is this. If you know that you're producing a certain number of moles of a gas under certain conditions of pressure, temperature, and you have a given volume to occupy, it means you can calculate what volume it'll be. You know what kind of vessel, what size vessel you're going to need. If you have a particular size vessel and you need to know under what condition of temperature this number of moles of gas will work in this vessel, you can calculate that. So basically you can calculate any of the factors, volume, temperature, pressure, and number of moles from the other 3. Page 345. Okay, so a sample contains 4.38 moles of some gas at 250 Kelvin, has a pressure of 0.857 ATMs. What is the volume of the gas sample? Easy enough, because we know that PIV equals nert. So much fun. I just love it. But that's because I'm clearly a Fruit Loop. As always with anything, it really helps to list your variables. And we're told that the pressure is 0.857 ATMs. We want to know the volume. That's our unknown. We know that it is 4.38 moles of this gas, and the temperature is 250 Kelvin. Just like with combined gas law, these only work in Kelvin. You can't do these in Celsius. You'll get the wrong answer. And since we're working in atmospheres, our gas constant is 0.0821 ATM liters over mole kelvins. Okay. We are solving for volume. Pretty easy. So volume equals NERT over P. Okay. Volume is equal to 4.38 moles times 0.0821 ATM liters over mole kelvins. There's a reason for writing those units when you do this. Times 250 Kelvin all over 0.857 ATM. 0.857 ATM. There's this neat little thing, we haven't done a whole lot of it in here, but it's called dimensional analysis, and we do it a lot in physics. If you have all your units in a problem like this, you can do this handy dandy little thing of saying, oh, okay, well, moles divided by moles, moles cancel. Kelvin divided by Kelvin, that cancels. ATMs divided by ATMs, that cancels. What units are we left with? Liters. If you didn't do your algebraic rearrangement right, this will show you, because you will end up with you'll end up with a unit you shouldn't. Okay, so we get 104.900, blah, blah, blah. We have 3 sig figs, so this would just be 105 liters would be our volume. Easy enough? Ideal gas law equations are just algebra and plugging in numbers. It's really, really straightforward. Okay, so assigned, this is the chapter, this is the chapter review for chapter 11. Numbers 16 through 19, parts A and C only. And 19 and 20 are kind of challenge problems. So if you get through 18, then we'll talk about the other two. I want to see if you can figure it out on your own. But I'll give you pushes out of the mud on those. So get through 16, 17, 18, and then we'll talk again. That's it.